Okay, and now we're back with Unit 4, Day 3, finishing up. We stopped in the middle because we had a little bit of technical difficulties. Now we are going to look at something called a perpendicular bisector. Now this one is like a combination of your altitude and your median, okay? And so a perpendicular is going to tell you that you're looking for right angles, and you see them. But something special about these is that not only do they make a right angle, they also go through this midpoint of this side and make congruent pieces. And so it's a perpendicular bisector. Now, sometimes you get lucky, and the perpendicular bisector is the median. It goes through that third side. But most of the time, this perpendicular bisector does not go through a vertex. It makes the right angle, check, that's perpendicular. It makes the bisector because these two sides are congruent, check. But this vertex is not guaranteed, okay? So it may not go through it. These three pieces also always meet at a point of concurrency. No matter how goofy or scalene your triangle is, these will all three always meet at the same spot here. And this is called the circumcenter. The circumcenter is the point of concurrency for your perpendicular bisector. Fun facts about the circumcenter. First of all, it's always equidistant from the three corners. And since it's always equidistant, that's like the radius of a circle. So the circumcenter is the center of a triangle that goes in circumference of or circumscribes this triangle. Isn't that kind of goofy that, yeah, randomly perpendicular bisectoring all these sides is going to find you the middle of the circle that goes through those three vertices. Kind of a fun fact. Probably gets used a lot when you're trying to create things in machinery and you want to make sure that things are going to be balanced, okay? But for us, we're more just interested in knowing that this perpendicular bisector makes the right angle, bisects the side. This is the circumcenter, so it will be the same distance to all those corners because all those corners are on the circle. Your visual hint, if you're trying to tell, what do I have? Is this an altitude? Is this a median? Or is it a perpendicular bisector? Well, if it makes the right angles, check. It could be an altitude, or it could be a perpendicular bisector. So what you're going to do is you're also going to then look to see if it cuts sides in half. If you see these congruent pieces, then you might think, well, it could be a perpendicular bisector, or it could be a median. And the way you know you've got a perpendicular bisector and not just a median or not just an altitude is it's going to be both. It's a combination of the two. It is perpendicular like an altitude and it makes the side congruent like a median. You know it's not the median if you don't go through here. So if you don't come from the middle to the angle, you can automatically eliminate that it's the median, okay? But if you've got these congruent pieces, you're going to want to make sure you're perpendicular and be sure about it. Don't just trust the picture. You look for that symbol or something telling you it's a right angle to make sure that it's your perpendicular bisector for your triangle. Okay? Grab my little mouse here. Oh, it cooperated better this time. Good on it. Now we have angle bisectors. Angle bisectors are exactly what we've known this whole time since the start of the year, okay? It bisects angles. So you've got a segment that's in a vertex, because those are the only angles you got in a triangle, are those three. Starts in the vertex, and it cuts the angle in half. Somewhere down here, it's going to cross the other side. We don't know anything about that. All we know is that the angles are congruent. The angles being congruent doesn't tell us anything over here. It just tells us that those angles are congruent, okay? And so we've got our angle bisector, bisects an angle. There are three angle bisectors, and you can tell because there are three angles, all right? The point of concurrency for all three of these, come here, buddy. Let's try again. You're supposed to wake up on a click. There we go. These intersect also at a point of concurrency called the incenter. And guess what? That's the center of a circle inside the triangle that just touches the three sides. Well, that tells us that this incenter is congruent equidistant from these sides at the right angle. This length and this length are not the same. But if I were to draw something perpendicular to each side, it would be the exact same distance. Fun fact, not one you have to know. I'm interested in you knowing that angle bisectors intersect at the in-center. Okay? And you can come up with whatever helps you remember that you want. How do I know, looking at a picture, if I have an angle bisector? I'm going to look at and see in these vertices, got to get the plurals right, if these two are the same size, or if I end up finding out that they're the same size. This is where drawing your own pictures is really helpful. If I see that these two pieces of this angle are congruent, I know that whatever segment I have here must be an angle bisector, and so these must be congruent angles. Okay? Lastly, but definitely not leastly, we have a mid-segment. And once again, I forgot to make these pop up, so you get to see them all up in front. A mid-segment connects the midpoints of two sides of a triangle. Well, if it connects midpoints, that means this piece and this piece are congruent, and this piece and this piece are congruent, and I have connected them through somewhere inside the triangle. Okay? Fun fact about the mid-segment that we're going to use. It's always parallel to the third side. So you're connecting two of the sides at their midpoints, you're automatically going to be parallel to that third side. Maybe at some point we'll try proving that just for giggles, but for now you get to trust me. Good times, right? It's parallel, and then you'll notice that, well, if I'm connecting midpoints, I'm not going to have a point of concurrency for these mid-segments. It doesn't exist. Instead, these three mid-segments you get from connecting the midpoints of the three sides create a fun little triangle. And here's another fun fact about this triangle. This triangle and the other ones are all exactly the same size and shape. They are congruent triangles, which again, I could show you, I could prove it, but for now, you're going to trust me and just use that fact instead on some other stuff. Okay? So, looking at these pieces now, let's see if you can sort them, or if we can sort them together into their different places. So here, come here, where's it? Oh, I saw it, there it is. So this, you'll notice in this triangle, I've got something going through a vertex, and oh look, I have two congruent angles. If I have congruent angles, that makes me think of an angle bisector. So this, oops, I forgot I have to take it out of presentation mode in order to drag stuff around. So let's see if I can at least get back to that and point it out. There we go. So this right here, you would want to file under an angle bisector. This guy right here goes through a vertex and is perpendicular, even though it's laying on its side and it's in that big glare spot. I see that it's perpendicular, but I don't have anything saying that these are congruent. So it's perpendicular, but it's not a midpoint. So it's not a perpendicular bisector, it must just be an altitude. Down here, I'm going from a vertex down and, oh look, congruent sides. This is a midpoint, which means this must be a median. Here, I'm going from a vertex, making a right angle. Right angles make me think altitude. And so I know that this piece here is an altitude. This is the kind of distinctions you're going to be making over this next assignment, next section of the lesson. So here, if you're looking at our pieces, and I'm missing some pieces here, if you have an altitude, its point of concurrency is here in this middle. You try and think of where that's going to be, and whether it would be the orthocenter, the incenter, the circumcenter, or the centroid. And you would need to be able to match all these up. Again, since I can't drag them, I'm not going to waste your time because, you know, you're not going to be doing that so much. You've got flashcards. Oh, I made one of them pop up. The angle bisector popped up. Good on me, Mom. Come on, buddy. Yes, I see you there. We're going to move on now. Come on. There we go. So just a little bit of work on the math of triangle midsegments. So the theorem, the triangle midsegment theorem, is what I mentioned before, is that if you've got a segment connecting these midpoints, it's going to be parallel to this opposite side. And then fun bonus fact, it's half as big, which makes sense because we have gone halfway up the sides of the triangle, and so this has shrunk to be half as big as this other side. you can use all these facts to figure out lots of numbers and things. So for example, I have this right here, and I'm going to tell you, okay, then this segment must equal this segment if it's a mid-segment. This one must equal this one. CD must equal DE. I also know, if I know that I have a triangle mid-segment, that these two guys must be parallel. Okay, just because I tell you it's a mid-segment, that's what those do. And I know that this guy is half of AE, which means if you flip it around, that this bottom piece here, this base, must be twice the size of my mid-segment. Knowing all these numbers, we can figure out some things. I tell you I have a mid-segment. Well, what will be the length of BD? Well, you think, well, if I have a mid-segment, it's automatically half of its parallel side, so it must be 24, because mid-segments are half of their opposite side. Going the other way around now, how big is AE going to be? It's going to be twice as big as the mid-segment parallel to it. So if this mid-segment is 12, this side must be 24, because it's always going to be twice as big as its mid-segment. Okay? Moving on, I give you that this piece is 4, and I give you that this piece is 6. And I'm asking, what is the length of CE? I want to know how big this whole piece is over here. Well, this is where you have to think, oh, mid-segments go through midpoints. This piece and this piece must be equal. If they're equal, this must be 6, which means CE must be 12. And again, that's just using those properties of our mid-segment and using our algebra to figure it all out. We can do the same thing. What is this length of BC? Knowing that this is bisected by a mid-segment, I can know that BC equals BA, which is 4. Okay? So we're just using these properties over and over again. You can do one that involves algebra if you want. I can say this is 3x minus 2 and this side is 20. You can use those properties to find x. You think, okay, if it's a mid-segment, then this piece must be half of this one. Or, in other words, you could think that, oh, 2 of these have to add up to 20, okay? And if I do that, 2 of those 3x minus 2's adding up to 20, algebra, I'm going to divide both sides by 2, add 2 to both sides, x comes out to be 4. And then if I put the 4 there, just to check and make sure everything really works, 4 times 3 is 12. 12 minus 2 is 10. Oh, 10 is indeed half of 20. So the number I found works. Find the measure of angle CDB, this angle right here. Well, remember, these guys are parallel to that side. And so if these are parallel, this becomes a transversal, cutting across those parallel lines. So this 65-degree angle and our angle CDB are corresponding. Corresponding angles for parallel lines are always going to be congruent. Therefore, CBD had to be 65 degrees because parallel lines imply congruent corresponding angles, which is what we did in our last unit. Okay, so knowing all that, I hope you feel a little more informed about the different special segments in a triangle and the fun things you can do with them. You're going to have some practice assignments. Good luck. Have a great day.